let's work on this optimization problem. A rectangular storage container with an open top is to have a volume of 16 cubic meters. The length of its base is twice the width. Material for the base costs $11 per square meter. Material for the sides costs $4 per square meter. Find the cost of materials for the cheapest such container. I'm not a big fan of the English part of this problem. As English as a second language person, I always struggle to understand complicated phrases if they're involved in the homework problems. So let me help you to see the way I see those problems, how to figure out the important part right away, especially if you see problems like this on the test when you need to be fast. So sketch the picture. That's the first thing I would do. I see rectangular storage. I sketch the picture. If you don't know how to do the fast sketch of the rectangular box, ta-da! See, I'm very fast. I have to say I practiced a lot as a student. But I have a prettier picture for you on the right. Now it has no top, right? So this thing is completely missing. That's fine. Then the volume, let's write down right away what we have, is 16 meters cube. Okay, we got that. The length of its base is twice the width. I don't have variables for it, so let's figure out some kind of variables. Let's denote, let me write down. Let W be width. That's a classic way to do it, but to be honest, you can do X and Y if you want. H to be the height, and then L to be the length. So to be honest, again, you could have X, Y, and Z, for example, even the Y in Z is height, and so on. You choose whatever you like. X, Y, and Z. In this case, I decide to choose width over here, height as height, and then L as length of the box. Good. Then I can see the phrase that the length is twice the width. You see, that's a kind of weird English phrase, but it's fine. The length is twice longer than the width. Okay, I got it this time. So if you don't understand it as well as some other people around you, don't be afraid. It's very normal. I will write down that length is 2 multiplied by W, right? I'll put the notation in the box, and I will write down the knowledge, which is basically the data we have, something, whatever is given. L is 2W. So now we can write down everything in terms of W. That is good because we have relationship between L and W. Material for the base cost $11. Oh my goodness, the cost is now involved. It's fine. Let's write down what does that mean. So the material for this base, so let's write down the cost for the base is $11 per meter squared. So that means this base will have the given price of $11 per meter squared. Material for the sides, C sides, is $4 per meter squared. So the sides are, how many sides do we have exactly? Correct, 4. And you can see, remember, we don't have the roof, so that's why we only have cost for the base. And then 4 sides, $4 per square meter. Find the cost of materials for the cheapest such container. So basically this phrase means minimize the cost, right? Because we want the container to be the cheapest. Okay, fine. So to minimize the cost, it means even though the volume is given, we don't know the height, the width, and the length, and that's what can be changed. So this box also might be the same, having the same volume as 16, but now the sides are very tall. If the sides are taller, that actually might make it cheaper because sides have cheaper material than the base. Probably the base need to be stronger to hold something in the box rather than sides just creating a structure. So that's kind of my intuition. Probably we need to shrink the base, but not too much, or else it's going to be a weird looking box, like so super tall with barely any base. So it should be some kind of optimal solution. The most important to understand is what is our objective function, which means what do we need to minimize or maximize? So let's write down to minimize. Did you understand what are we minimizing? Cost function. But cost of what? We have different costs, so I don't really understand which exactly we are minimizing. Probably total, right? Total cost to build the box. So that's why they did not mention it exactly. So you could think about it. So the total cost will need to be created. The function of this total cost, let me just call it cost. Let me just call it actually C with no subscript. C total, or just C, will be cost of the base plus cost of all the sides, right? That makes sense. And then the total cost also depends on how tall and wide those sides and the base. So the measurements or dimensions of each element here, which is sides and the base, blah, blah, blah. Let me start actually performing calculus for you. So first we need to figure out, I would start with objective function, but I can see the students like to write down something that is easy first. And the easy in this problem, let me do solution here, before we just collected the ideas and data. The easy in this problem is to figure out the volume, because we know the volume of the box. The volume of the box is what? Correct. It is length times width, right? And we can write it down as width is length is twice of width times width. Did I miss anything? Exactly. Where's the height of the box? So if you mention it out loud, you did good. Let me multiply everything by h. So now, instead of 3 variables, we have 2 variables because W and L had some kind of relationship. So we have 2W squared times h. And that is what? 16. Those are our constraints. Now, let's write down the objective function. The objective function will be the cost function. The cost function is 11. Let's start with the base. $11 per meter squared. Those are money, right? So dollars. Meter squared is gonna be coming from the dimensions of the box. So, well, let me do total. And this total here, this cost will have measurements of the base and sides. So I need to figure out the size of the base. Well, that comes from geometry as well. And that is length times width, right? I can even write it down here for you. So area of the base is length times width, which is 2 width times width, which is 2 width squared. Let's do that. 2 width squared. That's the area of the base. Plus, now we have the other cost, 4. Those are dollars as well, times, and now we have sides of the box. And the thing is that they are not the same. So I'll open the brackets, and then I'll write down, those are sides. We have 4 sides, 2 and 2 are the same. So we will have, let's say, area 1 and area 1. And then the back will be area 2 and the front is area 2, right? And we can add up those things together. So let's do that. Maybe I'll change the color for you. What is the area of this beautiful side on the right? It is height times width. So let's write this down. Height times width, and there are 2 of them, right? So times 2. Plus, what is the area of the front or the back? Well, this one will be 2 widths times height, because it's length times height this time. So it's gonna be 2 widths times height And there are two of them as well. So I will do left and right, front and back. Close the brackets. This is the objective function basically, and this is what we hope to minimize. So this is the system, and I will make notes. Constraints means restrictions, and then objective function to minimize. We did not start calculus yet, because calculus is when we start taking derivatives and using a first derivative test or second derivative test, but we did not even reach that moment yet. So I don't like that we have two variables for cost function, w and height. It would be nice to solve for one of the variables from the volume equation. Volume is 2w squared h, and it is 16. So from here, let's solve for one of the variables. Let's solve for h. H will be 16 divided by 2w squared. Now we have a relationship between h and w, and we can even simplify it. It is 8 over w squared. This does not make sense if w is 0, but we can assume that all the variables over here are positive. Positive, positive, positive. Sometimes people do positive or equals to 0, but in this case, and then they say, well, if the sides are 0, there's no volume. In this case, we're just not going to allow it. W cannot be 0, so we don't divide by 0. So now, substitute this beautiful relationship of between h and w into the objective function. Everywhere I see h, I will now have 8 over w squared. So let me put it in red, because now it's getting more interesting. I have 11, I will keep the variables as they are to make it more visual. 11 times 2w squared plus 4, remember 11 and 4 were prices. 4 multiplied by h is, let me change it to purple, 8, purple and fat, 8 over w squared times w times 2. 2 were there because there are two sides, plus 2wh, h is 8 over w squared, times 2 again because we had two sides. Two sides from left and right, and two sides from back and front. Okay, well that is objective function. We want to differentiate that, but maybe let's simplify it, because it just makes sense. Too complicated. So we will have we have 2 times 11, which is 22, w squared plus, because w is not 0, I can actually cancel out some of it. So it's going to be 4 times 8 times 2. Maybe let's simplify that 2. That is going to be 4 times 2 is 16. 16 times 8, and I'm kind of too lazy to figure out the calculations here. I probably should have done it. Okay, fine. Actually, I was thinking to keep the 4 outside first. So it's going to be, yeah, because it's factored out, makes sense. 16 over w plus, same. Here, cancel out w because it's not 0. 2 times 8 is 16, but now it's also times 2 over here. So it's going to be 32 over w. And all of this is multiplied by 4. Well, okay, it's getting better. It looks much better now. Let's finish. C equals 2. 22 w squared plus, we have now 4 with common denominator w. 16 plus 32 is 48. C equals 2. it is 22w squared plus 192 over w. Yay! So this actually, the last line is the one I should have done in red. Everything else is intermediate calculation. This is the objective function to minimize. To minimize. Ta-da! Finally, the calculus starts. So if you want to know the steps, I would say step 0 or step 1. Write down the variables. Picture. Don't forget the picture, right? Picture. The visualization of those problems is very important. Step 2. Formulate the functions, which are constraints and objective function. Step 3. Solve for the variable from constraints. Step 4. Plug in into objective function, simplify. And we finished step 4. Step 5. Change back to black color. To find the minimum of this function, we're going to differentiate this function, which, by the way, depends on w now. Only one variable. In calculus 3, we will be taking derivatives of functions with 2, 3, 5 variables, and that will be super fun. 44w minus w squared is in the denominator, and then 192 is in the numerator. Was it too fast? Let me maybe make it slower. 192w prime is the same thing as to differentiate 192 multiplied by w to the negative 1 prime. So what is that? Negative 1 goes down, 192 stays the same, and then w now is raised to the negative 2 power because we need to subtract 1. But that can be written as 1 over w squared with a negative in front and 192 multiplied by it. So that is the derivative. We want to solve this derivative. We want to find w. Well, this derivative is 0 or does not exist. Well, to do so, I highly recommend to create a common denominator if you can. Now, if you see fractions, just create a common denominator. It makes everything so much easier. I really recommend that. 44w cubed minus 192, like so. Now, I want to see where the numerator is 0 and when its denominator is 0. Those might be our critical points. Well, w is not 0. We already made this restriction over here. Thus, there's no critical points from the denominator. We only need to solve 44w cubed minus 192 equals to 0, like so. That gives the solution. Let's carefully do that. 44w cubed equals to 192. w cubed equals to 192 all over 44. w equals not plus minus, just plus 192, 44, and that is a cube root. So this is our solution for what? Do you remember what w even is? That is the width. Well, actually, we don't know yet if this is the optimal width, but we know that it's a potential solution because it is a critical point. Remember, it only can be critical point if it is in the domain of the original function, which actually we never wrote down. What was the domain? So that will be your homework to figure out by yourself if you want to. The domain comes from these ideas. W cannot be 0, but can W be 1 million, 5 millions? No, because then H shrinks to 0. So there's definitely domain for W to make sure that the box makes sense, that it is a physical object. And we will have, let's see, the critical point. We kind of need to make sure that it is indeed the solution. You can choose what to do. I would not do the second derivative test. I would do the first derivative test. So justify, that will be our step 6. Justify that this width indeed gives us the global what? Minimum For what? Function c. So I will do the sign line for the derivative of the function. I will put a critical point here, which is a cube root of 192 over 44, which is apparently can be simplified to, did you try to simplify it? It is a cube root of 48 over 11, cube root of 48 over 11, divided by 4. Okay, makes sense. And we definitely know that w cannot be, so it's sign line for c prime, but the variable here is w. It have to be positive, so you can find a test point here and a test point after the point 48 over 11 cube root, and see the sign of the derivative of the function. What do we expect to have? If we know that we're looking for the minimum, absolute minimum, we want to have decreasing first. That means negative sign for the first derivative, and then increasing after that, and never change the direction again, which is true because it's the only critical point. And because we have negative derivative first and then positive derivative after that, and critical point is at this point, at the point that changed the sign of the first derivative, that is local minimum. To be global, we want to make sure it will never go down again, because what if it goes down even lower? Since we only have one critical point, it's also a global minimum. Thus, we can use it as the answer. Answer. W equals of cube root 48 over 11 is the input, right? The input of global, or the most minimum cost. But what is that cost? We actually never figured it out, and they asked us to do that. If you go back to the problem, it says find the cost of the material. And also we could actually find all other dimensions. You know, length is twice more than that, right? Remember that length is twice longer than width. Height can be found from the relationship we have from the constraints. Height is 16 over 2w. No, height is simplified to 8 over w squared. So it's going to be 8 over, and then 48 over 11 raised to the squared. So it's going to be 2 over 3. It was cube root, and now it's squared, because you can always write down w as 48 over 11 raised to the 1/3. So if it's squared, it's 2/3. And finally, the cost. The cost function can be found either from the very original equation with 3 variables, but it makes sense to use the one we have with 1 variable, because we put so much effort to simplify it. It was 22w squared plus 192 over w. So now, actually, I'm just gonna start the new one. W at 48 over 11, let's keep it as 1/3. Why not? Doesn't matter. Will be 22w squared becomes 48 over 11 raised to the 2/3 plus 192 all over 48 over 11 raised to the 1/3. You could flip this fraction and multiply it by 192 if you want. Just don't forget to change the sign of the exponent. I'm not going to be doing that. So let's see, some kind of mess up with parentheses. Let me erase this first parenthesis like so. 22 is multiplied here. And that is the final answer for the cost function. So it's actually what units they are. Units are in dollars. That is correct. Now, kind of don't understand how much money I need to go and pay for this open lid box? Well, apparently it is approximately $176.24. As you can see, I always put a dollar sign at the end, like units, and it's also just a popular way to do it in Europe. So that is a minimum cost of the box we are building with the given restrictions slash constraints. Oh, that was a long problem. So good job for watching this video. Practice a little bit more by yourself. I know these problems have many steps, including the reading English part, but we believe in you. You can do it. You're amazing. Be encouraged. Go get some tea or coffee and work more. Thank you for watching.